Okay, so this is going to be another semantic segmentation example that's going to expand upon some of the other examples, some of the other prior examples. We've seen some binary classification problems. We've seen a multi-class classification problem. And here we're going to look at training a model when we have incomplete training data. So we don't have a wall-to-wall masks, but we have a background class. It really just represents areas that weren't mapped but would fall into one of our map categories. Okay, so these data actually come from a prior study where we created this land cover map for the entire state of West Virginia. And we did this not using deep learning methods, but instead relying on standard machine learning and geographic object-based image analysis. So effectively what we did was we took all the images in the state, we turned them into blobs or segments using a segmentation algorithm. We calculated a bunch of statistics on those objects to become a feature space, and then we selected out objects to use as training features, and we trained a random forest machine learning model, and then we used that model to predict back to all the objects and did some post-processing to clean it up, and that yielded this data set. So if you're interested in this data, and if you want to read more about how it was created, this paper that was published in Remote Sensing, which is open source, and so you can get it for free, explains that process. Here's the paper, and also the resulting land cover data set is available on the West Virginia GIS Tech Center webpage. So it's this West Virginia spectral classes data. The land cover version just has some additional classes that were created with overlay, and then the forest fragmentation is a forest fragmentation surface that was created from the land cover. Okay, so anyway, that's the data. So let me talk about the inputs real quick. So the imagery that we used here is the National Agricultural Imagery Program. This is 4-band data, so red, green, blue, near infrared, and this data specifically represents the growing season of 2016, and it's a 1-meter spatial resolution. So from this data set, we went through and digitized a bunch of training samples, so you can see those here. So here we're over top of Morgantown. You can see the different training samples representing different classes. We specifically differentiated the following classes, so barren areas, crop, forest, grass, impervious surface, mixed developed, and water. For this actual classification, though, we ended up grouping the crop and grass into a low veg class because that was we had trouble separating those categories. So we have a pretty large training data set here, but as you can see, it's not complete. So obviously all these other cells would fall into one of these categories, but we just didn't map them. So it's an incomplete set. And also it's very imbalanced. Our state is it's between 70 and 80% forested. So a lot of the training data then are representations of forest, and also like a pasture and grassland. Those are the two most common classes. We have over 10,000 examples of each of those. But the other classes, we're looking at maybe a little over 1,000 examples of each. So it's an interesting problem for that reason. We also have this set of validation points. So these are point measurements that were collected randomly. So we created a bunch of random point measurements, and then we photo interpreted what class they fell into and used that as our validation set. And since these were created randomly, since they were created randomly, then the matrix, the confusion matrix generated would approximate the correct landscape proportions, or would be an estimate of the population error matrix. All right, so the data to run through this example is going to be on the West Virginia View website. Note that it's not in the process of uploading, so it's not up yet, but on this research page, there'll be a new button in this area that'll be West Virginia land cover DL underscore 5 meter. And this is specifically, we took all the NAPE data and we resampled it for 5 meters as opposed to 1 meter because all the image chips was like over 100 gigs, so we wanted to get a manageable data set up that people could use. So we resampled it, and we ended up with about a 10 gigabyte data set, which is much more manageable for download and whatnot. Okay. Yeah, so this is the explanation file comes along with it. So again, it just explains the data, what codes are assigned to each class, what different classes we're working with, and then it explains the data that we provided in the folders there, and then this links to the code. Again, this is on our West Virginia View deep learning example page, and all the code associated with this will be in West Virginia Land Cover DL. Yeah, so there's the code associated with this project. I think we're ready to basically get into it. Again, if you download the data from West Virginia View and then uncompress it, you're going to end up with a folder that looks like this. So in the chips folder here, we have all the image chips and masks, and we have some CSV files where we already broke them up into, randomly broke them up in the training and validation partitions. So that's the chips folder. The point validation folder, that's all these point locations, and we also have a copy of the land cover grid in there from the prior project where you can run like a point-based, create a point-based error matrix using those two data sets. And then the original training polygons are here. And then lastly, this example model prediction folder that has the model file, and then an example classification of a quarter quad, and then that actual quarter quad data. Okay, so I think we're ready now to move into our code and start trying to go through it. Okay, so I'm going to start off with this data chips prep. Oh, sorry. This data chips prep.r file. So here we're trying to get our data ready to generate by first generating masks and then taking the mask and images and breaking them into chips. Okay, so here I'm reading in SF, Terra, and dplyr. Dplyr is again for data manipulation, it's part of the tidyverse. Terra is for reading and working with rasters. FS is reading and working with vector layers as simple features. Okay, so first thing I do is I list all of the image tiles. Note that we're not giving you all the raw tiles because, again, it's like a couple hundred gigs of data, so that's just too much to transfer. So you can't really replicate this part, so this is just so you can see how we did it. So anyway, there's 1,831 quarter quads across the entire state. So we read a list of those files here. Note we use this pattern here, so it only pulls TIFF files, and all the folders are in subdirectory, so we do recursive equals true, so we get all the files and all the subdirectories within that folder. Okay, and then I create a new folder where I want to store the masks. It's this masks folder, and in that folder, I basically replicate the file structure that's in the original folder, so it has all the same subdirectories. So effectively I want two folders, one with the images and one with the masks, and they're going to have the same set of file names and the same subdirectories. And that just makes it easier for later. So that's setting up that folder. Next I define a function that goes through and generates masks. So the input for this will be a quarter quad of the 4-band imagery, and then next it'll get the and then also the vector objects representing the polygon training data. Okay, so here's the function we're defining. So it takes the image, the features, the field that specifies the code representing each category, what code to use for background, and then the name of the output. So first off, we read that image using the rast function from Terra. Then we read the features, the vectors, using the vect function from Terra. And then we get the extent of the image and convert it into a polygon. Then we crop out the features that occur within the polygon. So again, the features cover the entire state, but we want to be able to process it quad by quad. So effectively what we're doing here is just cropping out the features that occur in the quad. Now some quads may not actually have any features in them, so if they don't, then we'll just not do anything, but if there are features within the quad, then we're going to rasterize that data and then write back the mask. So note here I'm not writing back the image file because we already have it, we don't really need to copy it, we're not changing it. And so I'm just writing out the masks, and I'm only writing out the masks for tiles that actually have some polygons or training data in them. And then I apply that over all of the quarter quads. So again, we basically have a list of images here. They're in this folder. So we loop through, grab that image, grab an image, grab the features, tell it what field we're using, and this class value field has the numeric codes for the different categories. Set the background value to 0, and then basically name the output to the same as the input, but in the mask folder as opposed to the original folder. So anyway, that loops through and created all the masks. Now at this point, we have basically masks for entire quarter quads, and then also the associated imagery for the quarter quad, and they should have the same cell size and spatial extent. But what we actually need to train the model is individual image chips. So just like our other examples, we use our chipit function here to break that data up into chips. Here we're gonna spit back we're setting a size of 256 by 256, and then the stride is 256. So in this case there's no overlap. There's nothing really important here, really. Yeah, nothing super important that's different from what we did in any of the prior examples. I guess the main thing here is that we're only going to write chips out if they actually have a feature in them. So you'll see later when we actually go to train this model, it's just going to ignore 0. So that's not going to impact like the weight updates or the learning process. So if you have a chip that has no features in it, it's just zeros, it's actually not going to help. So we only exported out chips that actually had features in them. Okay, and then next thing I do is I list all the mask files, and I'm going to loop over those this time as opposed to the images, because there were some images that we didn't create masks for, because there weren't any features in the quarter quad, so we don't need to process those. So we just need to process the masks and their associated images. And then we just loop through that and create all of our chips. So you can see here we're setting a path for the input image, the input mask, reading those in. This is doing an aggregate, and that's because we want to aggregate the data to 5 meters pixel as opposed to 1 meter, just to save space. So this aggregate function is doing that. And then after that, we just run it through our chipit and get back our results there. Okay. So anyway, I'll show you what that produced. Again, you can't run this because we didn't give you the raw data because it's a lot of it. So what that created, if we go into one of our folders here, so this basically created everything in this chips folder. So we have all of our little image tiles, and these are exported out as TIFF files, and then we have the associated masks, and those are just one single band TIFF files. And you can see the size of the data set here, 24,180 images and associated chips. I note that you probably could, to save space, produce these chips using a compressed file format, so something like JPEG or PNG. Okay, and then I set the working directory to point towards the data, the folder, the directory that stores my data in it. And then I called the two CSV files as Panda data frames. So let's just run that real quick. See what we get there. Again, these were the R splits. You can make your own splits if you wanted. And I like working from data frames because I just find it intuitive. There's other ways to do it. Okay, while that's running, again, just a few other things. Here we're just setting some variables. We're setting our class mode to multi-class because that we'll need that for running those segmentation models. We're going to use ResNet 34 backbone. We're not going to use any pre-trained weights. Here I created a list of all of our classes in the order of the code. So 0, 1, 2, 3, 4, 5, 6, 7 corresponds to these categories. And then we're going to get lodges back, so we're not going to use an activation function at the end. Okay, so I'm going to run those. And then we're checking, make sure our GPU is being sensed and is available. So I got one GPU, everything looks good there. And again, I'm subclassing now the dataset class from PyTorch to load my specific data. Just a couple different things here than what we did before. Again, you have to have the init. That should basically return like an object that lists out all of the features that you could potentially read. And this we're doing with a data frame. And then the get item is how it's going to read and process a specific item or specific image mask pair. And then the length function there is going to return, or I guess method, is going to return the length or the number of samples. So inside of the get item here, a couple things. So I basically get the second, so I use the second index here to pull. So this is the row represents what we're going to iterate on. So whatever row, and then this is 2, so that means column 3. So that's the column that has the path to the image in it. And then the third or 3 index or 4th column has the mask path in it. Okay, and then instead of using like OpenCV or something to read in the data, here I'm going to use Rasterio, and that's because these are geospatial raster layers. All the chips have like projection info associated with them. So I'm reading them with raster. That also can read in the 4 bands without an issue. So I just did that because it worked well for me. Okay, and then I read that into an array, and then I close it. Again, generally with Rasterio, if you open something, you want to close it afterwards. And then I set the data type to unsigned 8-bit. I do a transpose to change the band order. We basically are taking the first band and moving it to the back. And then this is the same thing, but for the image. So again, close it when we're done. So that reads in as an array the 4-band image and its associated mask. Okay, and then if we can apply some transforms using accumulations, which we'll look at below. So we basically apply transforms to that data, and then we want to turn it into a torch tensor. So this dot from NumPy converts that into a torch tensor. This again is for the mask, the same thing. So torch tensor, rescaling the image from 0 to 255 to 0 to 1, because it again as a float as opposed to an integer, because that's what NumPy expects, and then setting the mask to a long data type, so int64, and then using permute here to change the band order to what PyTorch wants, which in this case is going to be channels first. Okay, and then this is the same thing, just if we don't do any transformations, right? And then that's going to return back the image and the mask. And then again, we get the length. Okay, so anyway, that allows us to read in our data set, again, just subclassing out the PyTorch data set. And here I'm setting some transformation. So for the validation data, I'm just making sure this 256 by 256 and setting a resize there. Again, that's really not really necessary because they're all that already. And then for For the training data, just to create some more variety, we are applying some transformations. So we're doing some random horizontal flips, random vertical flips, and then some blurring of the data. So that's just setting up our data augmentation. And again, with albumations, it should do the image and the associated mask concurrently, so you don't have any issues with misalignment if the like the mask is rotated or the image is rotating and the mask isn't. Okay, and then we just call our data loader there, or sorry, not data loader, our data set function to load in our data from our CSV files. And as you can see there, we ended up with 19,344 training samples and 4,836 validation samples. And then we use the data loader. This is a semantic segmentation problem, and it's 256 by 256, so we can't make the batch size too large, so I just set that at 10. We're applying some shuffling, but other than that, it's pretty standard. So again, this creates our data loaders there. Okay, so I want to be able to create a bunch of metrics. The main difference you're going to see in this example is the way we do our training loop is going to be a little bit different, just because we want to have a little bit of control and whatnot. So what I'm first doing here is I'm creating this new function that takes the confusion matrix, and from the confusion matrix it generates a bunch of derived measures. So it's generating overall accuracy, and then recall for all the classes, precision for all the classes, and then combining precision and recall to get the F1 score for all the classes. This is all being done with NumPy. You could have done it with Torch. So here we're basically taking the sum of the diagonal and dividing by the sum of the table, and that'll give you overall accuracy. For recall here, we're taking a specific cell, so class 0 in this, or class 1 in this case, and then dividing by the sum of either a row or a column to get recall precision. And then once we have those values, we're just using those to get the F1 score per class. And then we take our results and we combine that into a pandas data frame, and we assign indexes to it, and that's what we write out. So we're going to use this in our training loop later. All right, the next thing I do is I create a model object. This time I'm using UNet++. I mean, you could try other things, UNet or DeepLab, V3 Plus, or whatever. I'm just using UNet++ just for the example. So we're using, again, our ResNet encoder, which we defined above, our encoder weights, which is set to none. We're not going to initiate this model on pre-trained weights like ImageNet weights, because it's 4-band and those are 3-band, which makes it kind of complicated, so we're just initiating from scratch. Plus, we have a fairly large data set. We're going to use batch normalization in the decoder along with encoder, which it does by default. We're telling it that the data are 4-channel and that there are 8 classes, and then setting the activation to the activation we specified above, which is none, so we'll get back the logits as opposed to probabilities using like the softmax. And then once the model is created, we push that to the device, so it's on the GPU. So that creates the model. Okay, and then we're setting up a loss function. So this is really important. So remember that our class 0 is background, but it's not a background class. It's just cells that aren't mapped that weren't within our training polygons. So we can't train on that because really those cells should be in one of our classes. We just didn't map them that way. So we're telling it inside of the loss metric here that we want to ignore 0. So we're ignoring index 0 or just the background class. So what that means is that whenever the losses are calculated, it's not gonna take that class into account. So it's not going to impact the weight updates and the optimization or the learning process. This dice loss function, by the way, is coming from the segmentation models library or package there. So inside here you can see they've defined some loss functions, and we're using their dice loss. So it's coming out of the segmentation models library. Okay, so that's super important to set the index there to 0. We also put from logits is true because you're not using a softmax or anything to get probabilities. So it's going to expect logits to come in as opposed to probabilities. Okay, and then we're setting up an optimizer with a learning rate here. Here I'm just using the stochastic gradient descent as opposed to something like Atom or something a little more complicated. And the reason why I'm doing that is because I'm just gonna I wanted to use a specific type of learning method that, I mean, it will work with Atom and stuff too, but it kind of is more intuitive if you don't have a learning rate that's constantly changing. For other reasons. So anyway, from the PyTorch optimization library there, and under learning rate schedulers, I'm grabbing this one cycle learning rate method. So what that basically does is it's going to oscillate the learning rate from a higher learning rate to a lower learning rate. And this has been shown to help things converge quicker. Anyway, it's kind of a promising way to potentially train. Anyway, so it's one cycle learning. If you look up some of the papers by Leslie Smith, they explain that in detail. But it's just a nice way to potentially get something to converge quicker by oscillating the learning rate. Okay, so anyway, that's setting that scheduler up. Okay, and then I create two empty data frames to save my metrics into. Here's the one for the training data, and here's one for the validation data. And you can see I get all the metrics that function above calculates, and also I'm adding on the loss there. Okay, and then I just need a few other variables in the loop here. So I need to get the number of batches. That's what I'm doing with length train dl dot dataset. So let me just call this really quickly so you can see what this is. Well, actually, I guess I could just run it. I realized I didn't run any of this. I need to do that real quick. So if I run this, this should tell you how many batches there are. There. So, yep. All right. There you go. And then epochs. And then this accum iterator, that is going to basically tell us how many how many batches will be processed before we try to update the weights, and we'll talk about that in a minute. And then the number of classes that we want to map, and then the device. And then we enter the training loop, and this looks a little complicated. I'm going to step you through it. Again, this was one of the main points of this example was to talk through a more complex training process. Okay. All right, so first off, we're here, this first for loop, we're iterating by epoch. So we're going to go from epoch 1 to epoch 20 there. And then within each epoch, we're going to initiate a new confusion matrix, one to store the training and the other to store the validation results. And it's 7 by 7 because there's 7 classes, and it's an int type because we're going to get back the integer values. So those will get reinitiated at the beginning of each loop. And then this loop, we're looping over the batches here using enumerate. So we're going to batch index, an X and a Y batch, and then enumerate through those. So first thing we do, and this is for the training loop, we push the batch, the X and Y data batch out to the device or the CPU. With the gradients being monitored, we make a prediction. Then note with this example, because we have a 0 class that's a background class, it's still going to be predicted, but we don't want it to be included. So we want to get the one that had the highest logic, but not including the 0 class to be the return class. So here I'm basically just removing, I'm getting rid of index 0 basically, so that we don't use the 0 class prediction. We just look at the actual class predictions. And then when we remove 0, we then get the index for the channel that had the highest prediction, which would be associated with a specific class. And then we take that result, and here I'm detaching it, pushing it to the CPU, converting it into an numpy array, and flattening it so it's just a one-dimensional vector. Because we dropped the dimension to get the indexes to line up, we have to add 1, so that's what I'm doing here. Right now we would have 0 through 6 as opposed to 1 through 7, and we want 1 through 7. So this gets 1 through 7. And then I push the Y data out to the CPU, numpy, flatten. Then using those two one-dimensional vectors of the same length, I calculate a confusion matrix with these indexes. Because I'm not including 0, it just won't include the 0 cells in the result. Now, with the predictions, there would be no zeros because we didn't include those predictions when we dropped that channel up here, but the zeros will still exist in the reference data. So not including it there means that that row/column is going to get dropped from the confusion matrix. Okay, and here we calculate the loss, and then because we're gonna actually optimize after multiple batches, we have to divide by the number of batches, so that'll be 20 there to adjust for that. And then here we do the back propagation on the loss, and then this schedule.step, that's doing a scheduling step to update the one cycle learning or change the learning rate. Okay, and then this is another kind of new component. And here what we're doing is using a process called gradient accumulation. So because the batch sizes are actually kind of small in this case, because it's a kind of a complicated problem, it can produce some instability. So one way to get around this is to have it only update the model after X number of batches. So here, basically, it's only going to do a gradient update with the a weight update with the optimizer if it's it's a batch of of a multiple of 20. So like after 20 batches, 40, 60, 80, so on and so forth. Or if it's the final one, right? Okay, or at the end of the final batch. So anyway, that's what's going on there. This blog really does a good job of explaining that if you're interested in that. So this explains what gradient accumulation is, why you might use it, and then an example of how to set it up. Okay, so the key thing there is we're not updating the weights after every batch. We're only going to update it after every 20 batches. And then once we've done that gradient update, we zero out the gradient there so we can run the next loop. And then also at the end of each loop, we take our confusion matrix that we got for that specific batch, and we add that into our initiated confusion matrix up here at the top of the loop. So the idea there is that every batch is going to add into the confusion matrix. So at the end, we should get our total count of cells within our training polygons in one single error matrix. Okay, and then for the validation component, it's effectively the same minus like the back propagation, optimization, and whatnot. So again, you're iterating over batches. We're making sure we're not updating any of the gradients since this is for the validation. So push to the device, predict those, remove the prediction for class 0, grab the index, flatten that out to a one-dimensional array and move it to the CPU as an NumPy array, add 1 to it so the indexes match up, push the reference data to the CPU, then NumPy, then flatten, make the confusion matrix, drop the 0 class, and then calculate our loss for the validation, and then accumulate all of our confusion matrices into one confusion matrix as it loops through. So this is the training loop for all the training batches, training loop for the validation batches, and then lastly here we have what's going to happen at the end of each epoch. Okay, so at the end of each epoch, we're going to take our combined accumulated error matrix and run our metrics on it. We're going to pin those to our metrics data frame. We may get some divide by 0 issues, so I do a fill NA to 0, so we just convert those into zeros. And then we do the same thing for, and then we append that result to, again, the full data frame and do the same thing for the validation set, and then we write that out. So effectively, at the end of each epoch, we're going to get a CSV file and then after another epoch, it'll overwrite that CSV file and add a new row to it that represents the results of that at the end of that epoch. And then instead of saving like a final model, I'm just having it save the model after every single epoch here. and then we could go back and look at our metrics and then decide which of those epochs we want to use and use that as our final model. So that's saving the model out, and then at the end of each epoch it's going to print the epoch, the training loss, the validation loss, and then all of our training and validation metrics. So that's a training loop, and the key things we were doing there that were different was we're calculating some custom metrics using our own custom function and accumulating all this information into a confusion matrix. We're also using a scheduler to apply one-cycle learning, and we're using gradient accumulation, so we only really updating the weights after every 20 batches as opposed to every single batch to potentially stabilize the model a bit. Okay, this took a long time on my computer. It took roughly a day. So if you do run this, expect it to take a while. Okay, so after we do that, we end up with a trained model, and then we can use that model for inference. So I'm just going to talk through that inference process. So again, same thing, we're pulling in all of our libraries. This is another Python script here. Setting our working directory, making sure our device is available, reinitiating our model, and then loading our save weights into that model, making sure we push it to the GPU. And then we create this inference function, which is similar to the ones we were using before. So we're reading in our data there, pulling out chunks of the data, predicting on it, and then writing it all back into the array with some overlap to deal with edge effects. So that's that function. And then at the end, we have a function and we can just run it. So here I'm just running that on top of a topo map and then getting back the prediction as a TIFF, and we should get values from our 1 to 7 range of values. Note here again, we're setting a stride of 64, so there's a good bit of overlap between the chips, and a crop of 70 to get rid of edges. It's gonna expect 4 channels coming in, right? All right, so anyway, that's not that different from our earlier examples. Okay, and then the last script that we included here was this point-based evaluation, which is pretty different. Okay, so what we're doing here is, let me pull up ArcGIS again. So again, we have all these point measurements that are point locations where we photo interpreted. So like, for example, that should have been water, right? And we want to use these to try to assess our map. So just so you could do this over a really large data set, we just provided our old output, which again was not generated using deep learning, and those point measurements, so you could run that process on that data. Okay, so here's how you would do that. So here I'm again reading in some libraries, dplyr, Terra, Caret, and RF utilities. Again, we're moving back into R now, as opposed to Python. We're using the RAS function from Terra to read in the land cover data set, or reference the land cover data set. And then we're using the vect function to read in our validation points. Okay, and then this extract function, what that does is it extracts out cell values at locations. So we're telling it, we're inputting the land cover and our validation points. We're telling it not to code that out as a factor. So it's basically what we should get back is a table that has the cell value or the code associated with each classification in this along with the validation points, which is going to allow us to have our reference and predicted values in the same table. This takes a little bit of time because it's a fairly large data set and there's lots of points that it has to intersect. Okay, and then while that's running, I'll just step through this. So again, the next thing we do is we define this as a factor. So it actually comes out as numeric. So we convert to a character and then to a factor. I had some issues getting it to read as a factor with like drop levels, so I just did it manually. So that's why there's that second step there. And then I take that object. So I take the validation points, convert that into a data frame, and then I get the predicted values and the ground truth out of that data frame. Again, I have to convert this into a factor, just as I did up here. So then I have two factor columns, numeric codes representing categories. I use the confusion matrix function to then create a confusion matrix from the predictions, and that's from the caret package. And then I use this accuracy function from the RF utilities package to get my assessment metrics. Okay, so let's run those through. This should be pretty fast now since we had that done. So again, we get our data frame here. Let's just look at that real quick. So here you can see we have a class code we're not using, the classified column, and then the ground truth there. Wrong one. Oh, there we go. And then convert here, and then convert or create our confusion matrix, and then get our accuracy metrics. And then you can see the confusion matrix there with the counts in it. And then if we do our acc out, oops, oh, there we go. You can see the validation. So we had an overall accuracy of 93.7%. That's not too bad. Kappa coefficient of 78.1. Here's our producers' accuracies and users' accuracies for each class. And then we have some other metrics down here. Also, I guess we didn't print those though. So again, with these users and producers' accuracies and with the confusion matrix, you got to get a sense of where the errors lie in the classification. Okay, so anyway, the goal here was to look at a process for training a deep learning model where you don't have a complete wall-to-wall masks. So you have to basically ignore a background class and the weight updates. So that was one of the unique components of this example. We also looked at using one-cycle learning with a learning rate scheduler, setting up a custom training loop, calculating custom metrics within our training loop, and then saving those metrics out to data frames. And then lastly, using R, we looked at doing some validation using an intersection of reference points and then a resulting classification, and then some accuracy assessment functions from caret, and then RF utilities.